Today we're going to do polynomial functions. Okay. So our learning intention is to understand key terminology regarding polynomials and how to sketch them. So some of us have done this in Year 10, but it's something to revise over. So as assess criteria is understand key terms regarding polynomials, know what a polynomial is, and being able to sketch a polynomial. So from our syllabus glossary, a polynomial is an expression of the form an x to the power of n plus an minus 1 x to the power of n minus 1 plus the terms keep going, so an minus 2 x to the power of n minus 2, an minus 3 x to the power of n minus 3, all the way to plus a2 x to the power of 2 plus a1 to the power of x to the power of 1 plus a0. Okay, and where n is basically a non-integer, so not a whole number. Okay. All right, so some examples of polynomials. You could get y equals x4 plus x3 plus x squared plus x1 plus x0, which would just be 1. Yep. Obviously, you can throw in some coefficients. Yeah, you can have polynomials that don't have any terms in between. So yeah, so obviously this does have x to the power 5, x to the power 3. That's fine. And generally, we write the polynomial from the highest order to the smallest. Okay. Okay. Some terminology that we need to be aware of. So an x to the power of n, an minus 1 x to the power of n minus 1, an minus 2 x to the power of n minus 2, continue on, is a polynomial expression, which we've expressed. All right. So when you have p of x, this has a degree of n, where n is the highest power. So you're going to polynomial and you have a degree of n, n is going to be highest power. So for example, if we go back to here, the highest power is 4, so this polynomial has a degree of 4. This one is a power of 6, so this has a degree of 6. Okay. an, n minus 1, an minus 2, a2, a1, a0 are called coefficients. So for example, all these are coefficients of 1. However, this is a coefficient of a half and a coefficient of 2 for this one. Yep. An x to the power of n is the leading term. So remember back in algebra, x to the power of 6 is a term, x squared is a term, even 1 is a term. So this polynomial has 3 terms, yeah, and the leading term is x to the power of 6. Yeah. This one has 1, 2, 3, 4, 5 terms, but the leading term is x to the power of 4. And here we've got 3 terms, but the leading power of here is a half x to the power of 4. An, which is the part in front of the x to the n, so whatever is your leading term will have a leading coefficient. Yeah. All of these were 1, but this leading term of a half x4, the leading coefficient is a half. And then obviously a0 is the constant term, the last term that has no x to it. So if an equals 1, then the polynomial is called monic. So that's very similar to what we already know. So the quadratic expression of ax squared plus bx plus c equaling 0, that's called a quadratic polynomial, and it's a polynomial of a second degree, because there's your degree of 2, and so it's polynomial of second degree, and this is quadratic, as we know. All right. Some examples. We want to state whether or not the following is a polynomial, and if it is, we're going to state the leading term and the leading coefficient, the constant term, and its degree. So we've got f of x equals 2x plus 3. Well, that's kind of in the form of a1 x to the power of 1 plus a0. So this is a polynomial. So it's a polynomial of degree 1. The leading term is obviously 2x. The leading coefficient is 2, and the constant term is 3. Leading term, leading of a constant term, and its degree. Yep. Okay. Here we have f of x equals x cubed plus 4x squared plus 5. So here we've got obviously a to the power a3 x3 plus a squared x squared plus a1 x1 plus a naught. So it is a polynomial. It's a degree of 3. The leading term is x to the power 3. The leading coefficient would just be 1. And the constant is obviously 5. Okay. Here we have f of x equals 3x squared minus 1 over x. And I'm just going to write this in index form. So let's say we've got y equals 3x squared minus x negative 1. Now if we go back to the original expression, that 3x squared kind of fits over here, and obviously that plus a1x is nothing, and plus a, we have no constant term, but then we have this x to the power of negative 1. So this in itself makes this not a polynomial. So this is not a polynomial. Okay. Once again, I'm going to write this in index form. So we've got x is a half plus x1 minus 1, or I can rewrite it in, I guess, descending order. So once again, we get 1, and now we've got a half. So this half makes it not a polynomial as well. Okay. This example, though, we get negative 6x to the power 3, a half x squared minus x to the power of 1 plus 1. So this is a polynomial of degree 3. The leading term is negative x cubed over 6. The leading coefficient is negative 1/6, and the constant term is 1. Alright. Here we have an example saying we want to find polynomial 2 if p of x equals x plus 2, x plus 1, x minus 3. So when we get this question, we're asking what does the polynomial will equal when we plug in 2 for x. So 2 plus 2 is 4, 2 plus 1 is 3, and 2 minus 3 is negative 1, so we get negative 12. Okay. Example 3, we get a polynomial. We've got p of x equals 2x plus 5, which is a linear or degree of 1, and we've got q of x equals x squared plus 4x plus 8, and we want to calculate a p of negative 1. So we're not going to worry about that for the time being. We're just going to plug in negative 1 every time that we see x So 2 lots of negative 1 plus 5. Well, that's negative 2 plus 5, so that's 3. So this polynomial at negative 1 would be 3. We've obviously got QA plus 2. So we're going to plug in, every time we see x, we're going to actually put in a plus 2. So we've got a plus 2 all squared plus 4 lots of a plus 2 plus 8. Right, well we can expand this. This is going to be a squared plus 4a plus 4. So squaring the first term, squaring the last term, multiply them together and then double it. And then expand this, we get 4a plus 8, and then 8 again. So we've got a squared plus 8a, 12 plus 8 plus 20 is our polynomial when we have a plus 2. Okay. Part C, we want to find T2 when T of x equals P of x plus Q of x. So we're going to add these together first. So P of x is 2x plus 5. And then we're going to add what Q of x is, which is x squared plus 4x plus 8. So collect like terms, we get x squared, 2x plus 4x is 6x, and then 5 plus 8 is 13. And now we're going to plug in 2 for every time we see x. So that's 2 squared plus 6 lots of 2 plus 13. So 4 plus 12 plus 13, we get 29. Okay. Now we want to figure out what t of negative 3 is when tx equals p of x times q of x. Okay, so we want 2x plus 5 on the outside. I'm going to multiply that by x squared plus 4x plus 8. Okay, so we're going to multiply this whole thing by 2x. So we get 2x cubed plus 8x squared plus 16x, and then multiply this whole thing by 5. So we get 5x squared plus 20x plus 40. Collect like terms. Okay, we get 13x squared plus 36x plus 40. So two polynomials, a polynomial of degree 1 and a polynomial of degree 2, multiplied together will give you a polynomial of degree 3. Yeah. Think of basic your index laws of yeah. So you're going to add the powers. So we get a polynomial of degree 3. We want to find out when t of negative 3 is. So now I'm going to plug in negative 3 every time I see x. Okay, so 2 lots of negative 3 cubed plus 13 times negative 3 plus 36 times negative 3 and plus 40 gives me negative 161. Okay. So last example of we want to sketch the following polynomials. Okay. So here I'm going to find my x-intercepts, and using the null factor theorem, x is, if this is all equal to 0, x here is going to be intercept's going to be at 0. Here it would be negative 2. This one will be negative 1. This one will be 1, and here will be 2. If we want to find the y-intercepts, well, we'll set all x's to 0, and if that's 0, the whole thing becomes 0. Okay, so the y-intercept is going to be 0. We've got 1, 2, 3, 4, 5. So this is going to be a polynomial of degree 5. Okay, so I'm just going to sketch it. Okay. So we got the origin. It looks like we've got -2, -1, 1 and 2. Okay. And basically what we want to do is we want to test the value of each side. Yeah. So for example, let's say we have -3. Okay. So -3, that's there. -3 plus 2. -3 plus 1. -3 minus 1. And -3 minus 2 gives me a negative solution. Yeah, so I'm down here. So I must come up this way. I must obviously turn here, turn again, turn again, turn again, and end up going that way. And so if I plugged in, let's say 3 for my x value, I should get a positive number. Yep, so I get a positive. And so that's how I sketch my polynomial. Yeah, so plug in different values to see which way the polynomial is going. Let's do the next one. So first thing I want to do is my x-intercepts. Okay, this is quite interesting. So we get this x minus 3 all squared and x plus 1 all squared. So another way I can write that is actually y equals negative x minus 3, x minus 3 because it's squared, and x plus 1, x plus 1. So I get x-intercepts of 3 twice. So I'll just write times 2 in the bottom here, and -1 twice. Okay. My y-intercept is what I want to find out as well. Okay. So that if that's 0 minus 3, so we've got I guess minus 3, minus 3. 1 and 1, so that becomes 9, so this is -9. Okay, alright, so far what we have is we have a y-intercept here at -9, we have an x-intercept here at 3, and an x-intercept at -1. Now these are, it happens twice here, and it happens twice here. Okay, so just ignoring that it happens twice so far, let's just plug in values for this side. So let's say x was -2. Okay, so -2 minus 3 all squared, and then we've got -2 plus 1 all squared. We get a negative value. Okay, so somewhere down here. Okay, we know it obviously cuts this axis. Let's try a positive value over here. Let's find out what's happening over here. Let's say x was 4. Okay, so we get a negative value here as well. Okay. You can obviously test over here, but what basically happens when it's a double, or when it happens twice, it's a double root, it's basically your function will come up and hit that x-intercept, but bounce off it. Yep, it will bounce off it. So far we have something that looks like this. Yeah, let's just plug in, let's say 2. Yeah, we get -9, which is the same as the y-intercept. So it looks like we get this kind of function. Yeah, so it bounces at -1, and it bounces off at 3 and cuts that y at -9. So that's how you would sketch your function. You'd find your x-intercepts, notice if it's a double root, find your y-intercept, test each side of the intercepts to see what the function does. Okay, and that's it. Thank you.